Hello, friends. Today we're going to be reviewing Unit 4 of AP Physics C Mechanics. This is my Unit 4, as it was given to me by my predecessor, longtime AP Physics teacher, reader, etc. And so what we've done is we've saved drag force that really should go in Unit 2 with dynamics. But the thing is, we need integrals. We need that type of calculus to be able to do this. And so it happens later in the year, and we include it with Unit 4. So this is drag, and then it's also center of mass and conservation of momentum. So let's begin with the drag. So first of all, in some turbulent systems, the drag equation looks like this: D equals 1/2 C rho A V squared. I call this the Crave equation because it kind of looks like it spells crave. So C is the drag coefficient. This depends on the medium, the surface of the object that's falling or moving or whatever it might be. Rho is the density of the environment, the air, the liquid, the water, whatever it is. A is the cross-sectional area of the object as it's moving through. And then V, of course, is the velocity. That's in some turbulent systems, high velocity, but most often what you're going to see is this type of thing, okay, where the resistive force is negative BV, where B is some constant and V is the velocity. So it's negative because the force is in the opposite direction. The resistive force is in the opposite direction that the velocity is. If you have a falling object, then the terminal velocity, in that case, mg, right, the resistive force is equal to negative bv. The resistive force and the gravitational force equal each other. If we set them equal to each other, then v equals mg over b. This is how you find the terminal velocity of an object, where this is, again, it's where the resistive force is governed by this type of function. Now, notice if we want an equation or a function for velocity as a function of time, we don't have that. Right? We have velocity in here, but we don't have time. And so here is the um, derivation for finding that. It's a derivation that does sometimes show up on the AP test. I know I put it on my tests. So this is what it looks like. We start with this. So if an object is falling, always a good idea to start with a force diagram, which I did not do here. Shame on me. Um, so if we have a falling object, then we know that there is the uh, earth force down and the resistive force up. So then in that case, we get mg minus r, g minus r equals ma. That's just Newton's second law. Okay, now we know that r is negative bv, so mg minus bv equals ma. Ma is equal to dv dt. That's how we define what acceleration is. Fine. So now what we're going to do is we're going to separate the dv and the dt. We get them on separate sides of the equation because what we're going to want to do is integrate. We don't want dt. We're going to want something that's just in terms of t. And so we get dt over here and we separate everything, right? dt ends up on this side and then dv ends up on this side, but I want v with the dv. So wherever the v is, I've got to somehow get it. So I'm manipulating the rest of the stuff just to get v with dv on that side, because when I integrate, I'm integrating with respect to v. So whatever v is has to be on this side with dv. Now, uh, so that's just a repeat, I think, of what I had before. 1 over m dt. Yeah, okay. So now when I want to integrate this, integrate this with respect to v, I can't do this right away. I have to use u substitution. And so I set u equal to this thing, mg minus bv. That means du is negative b, right? Du dv. If I take du dv, take the derivative of this with respect to v, mg disappears, and then negative b, so negative b. And so I get that dv is negative du over b. I don't know why that negative ended up there. Need to get rid of that. Okay, so dv is negative du over b. I need that because that's what I'm going to substitute. dv turns into this, right? This thing gets substituted in for dv. And then here on the bottom, this is 1 over u. Now I can integrate. And I'm skipping over to this side, moving around a bit. So negative b over m dt. So what I do is I take the negative b here and I multiply it to the other side. So I got negative b over m dt equals 1 over u du. Nice and simple on this side. Now integrate. The limits here is just from 0 to t. On this side, though, the limits, the initial value of u, the velocity initially is 0, right? This is an object that's dropped from rest. So the initial limit is mg, and then mg minus bv, where v is just the velocity at this later time, t. When I integrate this, this ends up becoming negative b over mt, and then natural log, right? The integral of 1 over x is natural log of x. And then I plug in, so this would be natural log of mg minus bv minus natural log of mg, but using logarithmic identities and properties, we can simplify it to this. Negative b over mt, so on that side. Now, in order to get to, I'm trying to solve for v now at this point. I'm just solving for v. In order to get v out of here, I exponentiate both sides. So e to the negative b over mt equals mg minus bv over mg. Again, I'm still just trying to solve for v, and now I'm going to follow this going up to here, right? So I multiply mg to both sides, just do a little bit of algebra, right? So then I subtract mg over to this side, negative, divide by b, factor out mg, and we end up with mg over b times 1 minus e to the negative b over mt. So let's think about this for a second. At time 0, uh, this equals 1, right? Because this is, yeah, so e to the 0 power is 1. So 1 minus 1, this is 0. So v initial, right, v at time 0 is 0. What does the function for this look like? Well, after a long time, after t, if t is very, very large, e to the negative, very large number, it's like 1 over e to the infinity, then this is just 1 mg over b. And so it's asymptotically approaching mg over b. By the way, that's what we came up with for terminal velocity earlier. Starts at 0, goes there. Key things on the tests, right? You want to note what these values are. This one is 0. It's coming from 0. You can label it as 0. But then we also want to label if there's an asymptote or other important value, initial value, we want to make sure that we label that. If you want an acceleration function, just take the derivative of this, with respect to t. So that's a summary of drag, right? And I went through that derivation because it does show up. It's a good derivation, practice derivation to kind of go through. Let's see. All right, so now momentum. We're thinking about momentum. P equals mv, very simple. Now, interesting to note, F net equals ma. What is ma? Ma is dv dt. And so m times dv would be dp dt. So F net is equal to ma, but it's also equal to dp dt. This is actually how Newton um, defined his second law. We do it differently because of pedagogy, the way we introduce ideas in the classroom, high school curriculum, etc. But when Newton defined this, he said the net force is directly proportional to the rate of change of the momentum of the object. Right? Conservation of momentum. Here's the whole idea. If the net external force is 0, then momentum is constant. If you think about it, that's just Newton's first law. Right? If the outside force is 0, then the velocity is constant. If the velocity is constant, the momentum is constant. Okay, and that's true for a single object. It's also true for a whole set of objects, which we'll see. J is impulse. Um, Personally, I don't like the term impulse. I wish it was just change in momentum. We could just call it change in momentum. Impulse makes the people think about force. So, impulse, impact, that kind of idea. So when you hear impulse, just think change in momentum. Just replace it in your mind. Algebraically, it's force times delta t. And then here, it's integral f of t dt. And so let's take a look at the units for this real quick. If we've got newtons times seconds, that is a kilogram meter per second squared times seconds. And the seconds cancel out, you get kilograms meters per second. And that is the set of units for momentum. So it works, right? Pay attention to the units. They work. When you have elastic collisions, an elastic collision is where the kinetic energy is constant. It's the same before and after. Sometimes you'll have a complicated thing where like they don't give you one of the final velocities. This is a handy little equation that showed up in a derivation that I did in the lecture. And if you're trying to find velocities, if you can pack this one away in your mind, it might come in handy in a complicated calculation. Okay, inelastic collision, all it means is that kinetic energy is not constant. If it's perfectly inelastic, it means they're sticking together. However, in all collisions, momentum is constant. Anytime you have a collision in a problem, you want to be thinking about that in terms of momentum. If it's elastic, great, you can use energy. But for that kind of an interaction, that kind of an event, you want to think before and after the momentum is constant. As long as there are no net external forces, right? But then even if there are net external forces, you can take that into account with the impulse, force and time, etc. If you have a series of collisions, so something like some mass, a series of particles hitting something to be calculated this way, V average is negative n over delta t, right? So n is the number of particles, and then the total change in momentum. Okay, and so the change in momentum is m delta v. That means that so m times the number of particles is going to be the total change in mass. Right? And so the mass, this is like the mass rate, the rate at which mass is hitting the object, and then that times delta v. This is going to give you F average. Notice how the units work out, right? Meters per second divided by seconds, meters per second squared times kilograms. So it all works out. Two-dimensional collisions, just a reminder that when there's a glancing blow, as they call it, right, two-dimensional, usually it's 90 degrees, unless they say something otherwise, right? The angles from each other, the angle of the resulting velocity vectors, the angle between the resulting velocity vectors, 90 degrees. If you have changing mass distribution, right, this is rocket science. Sometimes people will say like, hey, it's not rocket science. Well, this time it is. And so you got a couple of equations, relationships you're going to use. So T is thrust, R is negative dm dt, right? And that shows up here. It's the fuel consumption rate. So the idea here is that, it's like a stream of particles, except that the rocket itself is losing mass as time goes on. And so that's what R is here. It's the rate at which the rocket is losing mass. That times v rel, the relative velocity. So we get this equation as well. It means the same thing. That equals ma, right? And ma equals m times dv dt. Dv dt is the rate at which the velocity is changing. This acceleration. M is the total mass. Also, this equation comes in handy. A lot of this stuff is kind of like plug and chug usually, but we want to understand the concepts as well. The change in velocity of the rocket is going to be equal to the relative velocity times the natural log of the initial over the final mass. Okay. So your rocket science equations. Real rocket science gets more complex than that, but it's the basic intro. Okay, so center of mass, algebraic center of mass. Again, the way we structured our course, we cover algebraic center of mass right away in Unit 1, so we do something hands-on, create something. And the whole idea is that if I want to find the location of the center of mass, that's going to be in just meters. It's just a location. But mass has to be involved, right? So I have 1 over the total mass times uh, each individual mass times its location, right? You just kind of add all those up. What happens is the kilograms cancel out and you're just left with meters on the locations. The calculus version of this is that the sigma gets stretched out into a big S, and then you're adding up the location times the little piece of mass, the infinitesimal piece of mass that you're adding up. So 1 over m, that stays the same. Integral x dot dm, or x times dm. It's not a dot product because neither of these is a vector. Okay, so then um, different mass densities. You can have linear mass density. So this is the Greek letter lambda. That's m over L, also dm over dx. If you have a derivation that involves calculus, you may need to end up with the calculus version of this. So it's how much mass there is per length. So this would be like a rope or something like that. Actually, you could take anything and analyze it just in turn according to how much mass there is um, given any particular width, length, etc. Sigma is surface mass density, so it's two-dimensional. So it's how much mass there is per every section of area, or dMdA. And then rho is what we normally think of as density. It's how much mass there is per volume. And then the calculus version would be dmdV. Okay, so here's a derivation example. Imagine that there's a rod of length L, and the linear mass distribution is given by the function lambda equals alpha x, right? Lambda is linear mass density. And so alpha is some constant and x is just the location, right? So how would you know what the linear mass density is here? Well, alpha, whatever alpha is, times whatever its x coordinate is. Okay, so we start off with our function, with our basic formula. center of mass equals 1 over m integral x dm. Well, what is dm? So I go back, I'm looking at this, and this is going to be, lambda is dm, dm dx, right? And so then dm, this thing, I can substitute in lambda dx. I have to do that because I'm going to integrate x, but I can't integrate x with respect to m. So I need to get this in terms of x. I need to get it in terms of dx. All right, and so lambda also is alpha x. So it's a substitution game where finally now I have all the x's involved. I have to substitute in alpha x here because lambda is in terms of x. I'm doing this in terms of x. So I've got to make sure I've got all the x's in there down to the bare bones. I'm going to factor out the alpha and simplify. So I've got alpha over m integral capital L. So from 0 to L, I'm adding up all the mass, this whole area. I'm going to find the center of mass, right, with respect to that whole thing. X squared. So I take the integral, I get alpha over m x cubed over 3 from 0 to L. And then when I plug in 0, I get 0. Plug in L, and I get alpha over m L cubed over 3. Now, usually we're not going to want this in terms of m. We want to know the location. If I have m in there, then I don't really know the location yet, right? I can't put my finger on what the coordinate is. So now I need to find out what m is. But with m, to find the total mass, I just have to add up all the little infinitesimal pieces of mass. And I can do that using calculus, right? So dm is like the substitution I used before, lambda dx, 0 to L. And then from 0 to L, alpha x dx, that's what lambda is, alpha x. Take the integral, I get alpha x squared over 2 from 0 to L. So this is the total mass in terms of L, which is fine. As long as I know the length, then I can plug that in. This gets plugged in this equation. I plug this into here, and I end up with this. Simplify, you get 2/3 L. So at a place 2/3 of the whole length, that's where the center of mass of this object is. Just a sample derivation kind of practice. If you have a system of particles, Newton's second law holds the the mass, the um, m times the center of mass is equal to just the sum of m. It's like the equation we had before. We just multiply the 1 over m, the m to the other side. Also, the momentum, m times v center of mass. So you can find the momentum of the center of mass of a whole mass of particles, whatever they are. It could be like a solar system or something. And then, so you just take the sum of all the momenta, and then the mass times acceleration. So the net force is, again, you just find the mass times acceleration of all of the individual particles, add them together. And so what you end up with is that ma equals F net. And again, that's just Newton's second law. And then if F net is constant, right, or F net is 0, then the velocity of the center of mass is constant. And that's just Newton's first law. So you can have all kinds of interactions, whole systems of particles. But as long as you can keep track of the center of mass and analyze that, then you can analyze what are the outside forces, etc. There you go. That's our unit 4, drag, momentum, and center of mass. Thanks for watching. Don't forget to like and subscribe.